All right. Hi, everyone. So first, let me introduce myself. Tansu Dailan. I'm an LSSTC Catalyst Fellow at Princeton, and I'll be chairing this session. So this session is broken up into two parts, before and after lunch. So the first speaker of this session will be... Okay. All right. I was afraid I'm doing something. Okay, so the first speaker of the session will be Mariano Dominguez from IATE, UNC, and the title will be Finding High Magnification Fields with LSST.
Thank you, Simon. Can you hear me?
If you speak a little further away from the microphone.
Okay, now it's better?
Slightly better, yeah, as far as you can go. Yeah.
Okay. Well, I was saying I'm Mariano Dominguez from Córdoba in Argentina. I work on astrostatistics. And I would like to talk today about work in progress. Was recently started. It was intended as a poster. And the idea is to try to study the high magnification fields with the Robin data. Well, why and how to study these high magnification fields? Well, the presence of the massive structures like clusters produce gravitational lensing of strong lensing effects, which produce extended arcs, which are strongly magnified, and they're typically magnified galaxies, foreground galaxies between redshift 1 and 3 in optical bands. And this allows a lot of study. For instance, could allow to study the properties of the dark matter on these halos, but also produce ideal target for spectroscopic follow-ups. Well, typically these regions are found in line of sight to huge galaxy clusters, and also inspired by the simulation results. High density, large red galaxies, luminosity density fields are used. For instance, the typical example are the Hubble frontiers fields, which are very well studied. And this led us to the topic of this session, which is time-delay cosmography, which lensing transients. This method could produce an alternative results for the Hubble constant tension, and was developed by several collaborations successfully, Holikov, Stride, and Cosmogray collaborations. And also, it's possible to use lensed supernova instead of quasars, as was recently demonstrated by the Chef-Doll supernova by Kelly and collaborators, and also Goober. More recently, Rodney reported the discovery of a multiple image supernova, which is shown on this picture. There is a talk today about this, but this is on an example of the extreme time delay scale that could be found in massive systems. And the key point is, well, how to try to find these interesting systems. And here I will detour when I work with the Sync and Rubin data. I like to sync in the Hyper Subprime Strategic Survey Program has a testbed for viewing. And this is interesting because it's a survey with an 8-meter telescope, reduced with the same pipeline and producing similar data products like, for instance, cosmological products like weak lensing mass maps, photometric redshift, galaxy cluster catalogs, and have a complex mass and realistic mass. Therefore, using this data and data products derived, for instance, the weak lensing mass produced by Oguri et al., this mass map are built up on based on the shear catalogs, measuring the shape of the background galaxies and in the standard weak lensing limit using the reconstruction technique proposed by Kaiser square. And there's also it's possible to use another most modern alternatives. Here I show the total mass map in one of the fields of this survey. And the signal here coming from weak lensing maps is roughly proportional to the convergence. And the point here is similar maps could be will be constructed with standard products of the text TXT pipe. And this kind of map located in the red dots are, here I selected some local peaks on this mass map. And these are, there are different options how to filter this map or how to produce this map, but in a stream of the more important peaks, they are consistent between different selections. And if you could take a look at some of the image on these selected fields, you, for instance, for here I showed 3 of these 6 selected points that is above some threshold. The point is that you could locate some important massive clusters. Some of them were found by Miyasako et al. Looking for share-selected clusters. Some of these systems are also presented in catalogs, cluster catalogs has Camira. And of course, in the case of reading data, will be easily found by the RedMapper, Amico, and YOLO cluster findings. Obviously, this information could be combined with other sources coming from Sunay-Seldovich, Planck, and S4 data in the future, or X-ray cluster catalogs. The point is that is easily using the weak lensing maps and additional information has the luminosity density maps to find good high magnification regions where could be done the time domain studies in these fields. Recently, we appreciated the fields from the James Webb Space Telescope, and there are also predictions about multiple image systems like this on LSST. The strong lensing analysis of this kind of system produce a detailed map of the mass distribution for in cluster and could be interesting for studies of the dark matter distribution and properties there. And also there is a work, very interesting work by Tanja Petrushkeva recently that study the clusters in the Hubble frontier fields that could be found in the Rubin footprint. And she found that there will be a number of lensed transients could be found, and using the standard Bayesian strategy from observations of LST, it could be expected in one or more supernova lensed by this kind of system. But I think that this number should be taken as a lower limit. There also an interesting study on the statistical side by Huber that looking about the best observing cadencing for this kind of discovery, in particular for time delay measurements. The important results shown by Huber in this table is that cadence, the higher cadence that's shown in pink colors here, are superior and the best designed for the detection of strongly lensed supernova, because they have the most high value for the effective time and also cover a wide area. The important thing that this is on the statistical side, and this is dominated by the short time delays produced by galaxy lensing. I'm interested on repeat this kind of analysis, but on the high magnification fields. Basically, this result, the Faber says that the Rubins could be used as a discovery machine for lensing supernovae. But in order to increase the numbers, there should be done a follow-up observation of the supernova discoveries. But regarding the previous result by Petrushkeva and the recent discovery of the lensing on high magnification system, these rates could be enhanced by maybe a ground-based cluster survey following this system in time domain until new upcoming data from the Roman observatory arrives in the future. Therefore, I will make a brief summary. As I say, that this is a work in progress. Basically, I was developed a technique for found high magnification regions based on lensing mass map. Also, this could be added the information from gravitational lensing searching methods or tomographic reconstruction method. The important things, I was very happy to hear that there is a new simulation group, which is building lensed supernova data for Rubin, that because I was trying to do that using the Oguri data and the new one by Peter, but it could be nice to use these simulations in the high magnification fields, of course, and now and DC2 simulation for design and strategy optimized by the discovery of high redshift transients, different time, and not just only supernova, maybe also could be added the double lensed system that was Eric recently talked about it. And the important thing is try to decide if maybe some kind of deep drilling fields on extragalactic high magnification regions could be useful for detect more of these transients, or how to design a monitoring program for follow-up observation using other astrophysical observatories. Well, thank you so much to the organizer for this nice meeting, and I would like to hear your questions. Thank you so much.
Thank you, Mariano, for the nice talk. Okay, questions.
So both question and comment here. One of my reasons for organizing this meeting and chairing it is to find synergies between the different LSST science collaborations. And I am particularly excited when people say that they like high cadence observing strategies for LSST, and things like alt-shared rolling are favored, because of course, from the supernova point of view, we would certainly like more observations than once every 10 days on a light curve. So if Astrostatistics has not yet responded to the Survey Cadence Optimization Committee, or SCOC, request for feedback, please send them this feedback, because we will only second that input from both desk and probably also from SLSC. The LSST PCW is a couple of weeks after this in Tucson, and so we should really make sure that our voice is heard from the time domain community, and we want better cadence than all of these silly static science programs that just want wide area. But what actually is confusing me a little bit about this is you had comparisons with both Matra and alt-shared rolling there as well. So there is some trade-off where more area because you find more systems is useful versus having more cadence for the same systems. Can you give us a sense of where that trade-off lies and where it breaks down? Do you need, is it 4-day cadence is sufficient? And it's better to have 4-day cadence in, say, 20,000 square degrees versus 3-day cadence in 16,000 square degrees? Do you have any sense for where that might break down?
Was the question heard, or?
Sorry, could you repeat? I can barely hear you.
Okay.
Okay, well, I'll skip the editorializing. I'm just kind of curious as to what the trade-off is between area on the sky and cadence. Is it better to have something like 20,000 square degrees and find more of these systems with a lower cadence, or have a higher cadence with alt-shared rolling, like say a two-day cadence like you had, but find fewer systems? What is the actual optimization that happens from your point of view?
Yes, the point is here. I'm suggesting to try to follow up just a few fields. That's the main difference. The difference is not try to follow and find out, just concentrate on the system that will provide a higher redshift transients, right? That's the point, and then it could be certainly the point here is try to analyze how many of these fields is possible to observe, but the results found presently on here, I think that that's the will be similar, right? But I'm not trying to cover all the sky. That is an answer that I will try to provide, and maybe for the next meeting on that.
Okay, one more question.
This is Graham Smith, really responding to Gotham's point. For rare things like strongly lensed transients, a rolling cadence is a bad idea. Sorry.
Was the question clear? Is there a mic issue or? Mariano, can you hear us?
No, I can hear you, yes. Sorry, I have some issues with the Wi-Fi.
Okay, so let's try it one more time.
I'm not sure there's a need to repeat it because it was more a response to Gautam's question about the trade-off between area and cadence. And for lens transients, because they're so rare, in contrast to unlensed transient folks, we prefer area over cadence.
Okay, so Mariano, did you want to add anything or?
No, not really. Just
Okay. All right, thank you very much. All right, so let's thank the speaker again. Yes, so we'll have